Hi guys, it's Mrs. Rajewski. Nice to see you guys today. Today we're going to talk about sequences and their limits as well as the squeeze theorem. So let's get right to it. If you recall from our first year, a sequence is simply a list of terms in a definite order. So like 2, 4, 6, 8. This is a sequence. It's got a definite order. Now sequences, they can be finite or they could be infinite, and they could converge or diverge. So when they approach a finite value, we say that they converge. So here's some graphs of a couple of sequences, and you can see that for this first one, it's a decreasing function, and it's converging to a limit. It's this red line right here. So this function is getting closer and closer and closer to this red line. Over here, I've got an increasing function, and we can see that it is increasing or converging to a particular value. I don't know what this value is. It's just going to refer to it as a red line. Even an oscillating function can converge, and this is going to eventually approach a limit. But every sequence doesn't actually converge. One of them could go off to infinity, could get progressively greater. So here's a sequence that isn't actually going to converge. It'll diverge. It's going to not ever get to a particular limit. Similarly, we could have a function that's going to just get progressively smaller. It's never going to go to a red line, to a limit. Here we've got an oscillating function that is going to just keep jumping back and forth over and over this red line, never actually approaching it. So not every sequence is going to approach a particular limit. So how can you tell if it's going to happen? Well, a sequence, A sub n, has a limit for if for each epsilon that's greater than 0, so that's just the Greek letter epsilon, there exists a positive integer n such that the absolute value of that sequence minus this L represents the limit is going to be less than epsilon for all terms in the sequence, with n being greater than that positive integer n. Well, that looks crazy, right? Basically what it means is that for every measure of closeness, epsilon, so how close it is to the limit, the sequence's terms are eventually that close to the limit. So for every measure of closeness, epsilon, the sequence's terms are eventually that close to the limit. Now, there's actually a proof in your textbook that is interesting and worth a read. So that's in pages 57 through 60 if you're using the Hayes text. I know that sounds like a lot, but I do recommend that you go ahead and check it out. Basically, if a sequence converges, then its limit is unique. So the proof for that particular statement is on page 58. Again, I definitely recommend that you check it out. These are some of the limit laws for converging sequences. So ultimately, it's not possible for a sequence to have two distinct limits. It's just going to have one. These are pretty familiar, I would say. They look a lot like some of the other rules that we've used in the past, and they're kind of common sense, right? If you've got the limit of a couple of sums, then you could take the limit of each individual sum. If you have the limit of if you're taking the limit of a product, then you can take the limit of each individual factor, multiply them together. If you've got to take the limit of a quotient, that's cool. You can take the limit of the top, divide by the limit of the bottom. Easy peasy. So Archimedes of Syracuse actually helped to prove that the limit as n approaches infinity of c, a constant c, is equal to that constant. Oh my, I am just getting used to working with this new tablet. So we can use that the limit as n approaches infinity of a constant is that constant, and work with a limit that we actually know already. So let's say we have the limit as n approaches infinity of 1 divided by n. Now we hopefully all know that right away. As n is getting bigger and bigger and bigger in our denominator, the fraction value itself is going to start to approach 0, right? We love this one. This is like, we're going to use this a lot. It's like a dividing by n party. All right, so let's take another one that we've used. So let's take, we're going to put it all together. If p is greater than 0, then the limit as n approaches infinity of 1 divided by n to the p power. So as this value is getting larger and larger and larger, and we raise it to the p power, if p is greater than 0, well then this whole thing is going to get super huge. Oops, I forgot my infinity. I said it, I just didn't write it. And that is going to go to 0 as well. Okay, let's extend this a little bit further. If our constant is in between 0 and 1, so let's say, and then we can say the limit as n goes to infinity, and I'll write it this time, of c to the n power. If our constant is a number that's in between 0 and 1, so our constant's a little number, maybe like half or a fourth, and then n is getting bigger, so we're raising it to the larger and larger power. Well, this is also going to go to 0 if you think about it, right? If I raise something to the to the 10th power, the 100th power, but that something is small, my numerator is going to get raised to that power, my denominator is going to get raised to that power, and if it's in between 0 and 1, my denominator is going to be bigger. So again, this is going to 0. You can see that I'm kind of working to see how can these constants and the limits around these constants be manipulated. Okay, so what about the situation where our constant is greater than 1? Right, so if our constant is greater than 1, then what happens? The limit as n approaches infinity of c to the n. If our constant is greater than 1, then our fraction, or whatever, 2 raised to the 1/1,000,000th power, this is going to get huge. It's going to get really, 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 really ridiculously big. It's just going to keep growing and growing and growing. So this, I would say, equals infinity, equals, I don't know, does not exist even. I'd say it's never going to be a limiting number. It's going to keep growing and growing. The limit doesn't exist. And we would say that that diverges. Excellent. All right, so we've got the stuff we need to know. Now let's start using it. I think you guys are going to like this. So here we go with example number 1 in our notes. We're taking the limit as n approaches infinity of 4/5 to the n power plus 3 divided by n minus 9. So I'm going to use one of our limit rules. So I'll just go back and highlight it for you, which one we're going to use. I'm seeing that I've got a sum that I'm taking the limit of. So I'm going to break it apart into pieces that I'm going to take the individual limits of. Now, I'll be honest with you guys. I don't always write all the work all the way out like this because it takes a little bit. But for you, for this video, we will write it all the way out. So we've got the limit as n approaches infinity. I wish I had a stamp or something. I could just stamp that down because we write it so many times. 4/5 to the n power, right? Plus the limit as n goes to infinity of 3 divided by n. And I'm going to add the limit as n goes to infinity of -9. And I'll put parentheses around that -9. And, you know, I would really prefer it, actually, if this problem would have had brackets around it so I could see that we're taking the limit of the whole darn thing, not just the first term. All right, so let's calculate these limits after all. Let's see, 4/5 to the n power. Now we can use some of those rules that we just came up with. My constant, 4/5, is in between 0 and 1, and it's being raised to the n power, so this limit is going to be 0. Now over here, I've got 3 divided by n, so n is going to grow and grow and grow and grow and grow. That means my fraction is going to shrink and shrink and shrink until it becomes 0. And lastly, we've got the limit as n approaches infinity of a constant. And Archimedes of Syracuse told us, hey, if you're taking the limit as n goes to infinity of a constant, the result is the constant. So my constant was -9. And 0 plus 0 is 0. Minus 9 is -9. So this is our result. Not too shabby, right? I told you it wasn't going to be so bad. All right, here we go. Example number 2. Yeah, that's it. That was it. We're done. Woohoo! All right, example number 2, we're taking the limit of this whole entire quotient. Okay, we actually did this before when we were working with limits to infinity. Just make sure that you divide each term by the highest exponent of n and then apply our limit rules. Sweet. It's the dividing by n party. These are my faves. All right, here we go. I am going to take the limit as n goes to infinity. Ooh, I'm still in pink. Now my highest exponent of n is just a first, it's just a first power. So I'm going to take 6n and divide it by n to the first power. But I can't just divide 6n by n. I'm also going to divide 72 by n. I'm going to take 2n and divide it by n. And I'm going to take 97 and divide it by n. All right, it was a dividing by n party, and these n's are going to reduce down to 1. This is going to result in, well, let's see, the limit as, well, let's rewrite it. We'll be neat about it. I've got 6, oops, oh, Mrs. Ryeski. I have the limit as n approaches infinity of 6 plus 72 divided by n, all divided by, looks like 2 plus 97 divided by n. Okay, we could take this limit. The limit as n approaches infinity of 6 is 6, that was a constant. The limit as n approaches infinity of 72 nths, well, that is going to be 0, right? As n gets super duper big, 72 divided by a super big number is going to get closer and closer to 0. Down here in the denominator, the limit as n approaches infinity of our constant 2 is 2. And the limit as n approaches infinity of 97 divided by n, again, is 0. Gotta love those. 6 plus 0 is 6. 2 plus 0 is 2, and this is going to reduce to 3. Okay, so I just wanted to show you really quick what this graph actually looks like. So check it out. If we graph the original function, 6x plus 72 divided by the quantity 2x plus 97, and I also graphed our result, since it's the limit and it's getting closer and closer, we figured out that it was getting closer and closer to 3. So check it out. This red line is our original function. Here's our line 3. And as we get further and further away, so we can see more a larger and larger x value, okay? Check out what that red graph is doing. You see it? It's getting ridiculously close to 3. So as x goes to infinity, our n value goes to infinity, we are getting, look at that y value. It's growing slowly, but it's getting super duper close to 3. Isn't that interesting? So that's what this is telling us without having to do the graph. Fantastic. All right, let's move on to example number 3. Now this one, you see I've got our little group symbol on here. I want you to try it on your own and hit pause on the video and then check and see if you got it right, okay? So pause the video. I'm going to solve it now, but see if you've got this one. Okay. Did you pause it? Here we go. All right. So this one, again, with the quotient, I love to use that dividing by n party strategy. So I am going to divide every single term by my highest power of n. In this case, it's an n squared. So this is actually going to be a dividing by n squared party. Are you ready? Here we go. I've got the limit as n is going to infinity of n squared divided by n squared plus 5 divided by n squared, all divided by, well, I didn't leave myself very much room here. Let's tidy it up. There we go. 2n squared divided by n squared minus 3n divided by n squared plus 8 divided by n squared. There we go. Oakley dokley. So I am going to start to reduce here now. N squared divided by n squared is 1. N squared divided by n squared is 1. Nothing's going to reduce here, but 1n will reduce with 1n. That's going to give us an exponent of 1, and nothing to reduce here. Let's rewrite this problem. So I have the limit as n approaches infinity of, I'm making it bigger this time, 1 plus 5 divided by n squared, all divided by 2n, no, just 2, no n's, they canceled out, minus 3 divided by n plus 8 divided by n squared. Now, over here, you can see that I have paused, and I was thinking, wait a minute, what? It was because if I had a 2n, it was going to keep on growing. The whole point of this was to divide everything by an n squared, the highest exponent n, so I wouldn't have been left with any other n's in my numerator. So just be careful. All right, I think we are ready to take the limit. Here we go. The limit as n approaches infinity of the constant 1 is 1. The limit as n approaches infinity of 5 divided by n squared, my denominator is going to get super duper big, but my numerator is going to stay small, so that limit is going to be 0. Down below, the limit as n approaches infinity of a constant is the constant, so that's 2. Thank you, Archimedes. Then the limit as n approaches infinity of negative 3 divided by n, that's going to go to 0, and so will 8 divided by n squared. As you can see, this is going to reduce to 1/2. Did you get 1/2? I hope you did. I bet you did. Good job. All right, here we go. Example number 4. Woohoo! Yeah, fair note. This is going to take a bunch of space. So, write small, split your work up into 2 sides. There might not be a lot of room in your notes. I will do my best to be concise. So what's different about this one is that we have kind of a sum inside a radical. So now it's in the radicand. If we want to take the limit here, an interesting strategy is to use a great one, an interesting one. In fact, if you take the conjugate, I forgot the J in conjugate. Oh dear, Mrs. Ryeski. The conjugate binomial divided by the conjugate binomial, then you'll have an interesting one and also help you to take the limit. So you might be thinking, what in the world does she mean by that? No worries. I'm going to turn this into a fraction by dividing it by 1. So nothing crazy so far. And I am going to multiply by the conjugate binomial. So the conjugate binomial is the same first term, the same last term, just a different sign in the middle. So that's going to be the square root of n squared plus n plus n. Now I can't go around town just multiplying numerators by something that looks like that. I'm going to have to do the same thing in the denominator. So again, I'm going to multiply by exactly what I have on top, n squared plus n plus n. This same thing, just a different sign in the middle. And I've multiplied it on the top and on the bottom. So I've really just multiplied by a fancy one. Excellent. Okay, well, looks like I just made things extremely complicated. Okay, maybe I did. What I'm going to do, I know you're going to think this is crazy, but do you see it? I've told you it's everywhere. Hopefully you believe me now. It's the distributive property. See, I'm about to distribute and multiply these binomials together. Check it out. Here we go. So we still have the limit as n approaches infinity. I'm going to take the square root of n squared plus n times the square root of n squared plus n. When you multiply those square roots together, they're going to drop away, right? And we're just going to get n squared plus n. All right, now I'm going to multiply the square root of n squared plus n times positive n. So this is going to give me n times the square root of n squared plus n. Okay, not too bad. I've just distributed this square root to both terms in my second binomial. I'm done with this square root. Now for the negative n. I've got negative n times the square root of n squared plus n. That's going to give me negative n square root of n squared plus n. All I have left is to multiply negative n times positive n, and that's going to give me negative n squared. Woo-hoo-hoo! All right, it looks crazy. Now let's keep our denominator the same. It's just going to be the square root of n squared plus n plus n. Because we're multiplying it by 1, nothing's going to change here. Oh my goodness gracious me. Now we can simplify this. One of the nice things about it is that it can be simplified. Check it out. We have n times the square root of n squared plus n and negative n times the square root of n squared plus n. So these are opposites. They make 0. Also, I have n squared minus n squared. Fantastic. All right, so this is actually not looking so terrible after all. That's the nice thing about multiplying by conjugates, by the way. And I know some of you remember the rules for conjugates, and so you were able to jump to this result immediately, and I love that. All right, so let's see, what do I have left? Ho-ho! I've got n left. N divided by the square root of n squared plus n plus n. Ooh, let's extend my fraction bar here. Oh my. Okay, so this is still kind of interesting. Okay. Well, I see that my highest exponent on n is 1, so I can try my dividing by n party. So let's try that. So dividing by n party. Let's see, I've got the limit as n approaches infinity of n divided by n. Now dividing by n is the same as multiplying by 1 over n, so in the interest of not creating some crazy looking fraction, I'm just going to do that. And then plus n divided by n. Okay, Okay, and let's see. I'm going to do an aside for logic right now. So let's do that in green. I'll call this the aside for logic. And let's work on that over here. So let's make some sense. Okay, we've got 1 over n, right? What can we take the square root of that would equal 1 over n? Well, if I had 1 over n squared, its square root would be 1 over n, right? Isn't the square root of 1 over n squared really equal to 1 over n? So instead of writing this 1 over n, couldn't I in fact write the square root of 1 divided by n squared? Yes, I can. And that's exactly what I'm going to do. So for my aside for logic, instead of writing this 1 over n, I'm going to write the square root of 1 divided by n squared. Are you ready? Hopefully I didn't take you to crazy town. And I'm going to reduce here while I'm at it. So I've got the limit as n approaches infinity of 1 divided by, not 1 divided by n, no, remember our aside for logic, I'm going to use the square root of 1 divided by n squared. And I'm going to multiply that by the square root of n squared plus n. And we're going to add that 1 there because remember n divided by n is 1. I know you're thinking, okay, why did you even do that? It's because I really wanted to bring this 1 over n into my radical, and the only way I can do that is if it's a radical already itself. So now we're going to use the distributive property, and I'm just going to, did I say the distributive property again? Oh my goodness, twice, one problem, love it, it's everywhere. All right, so the square root of 1 divided by n squared is going to get distributed into this radical now. I'm just going to scooch this up a bit. All right, here we go. The limit as n approaches infinity of 1 in our numerator, yay, easy number. Now the square root of 1 over n squared times n squared, that's going to give me the square root of n squared divided by n squared. Plus, when I multiply 1, the square root of 1 over n squared times n, I'm going to get n divided by n squared, reducible, plus 1. And of course we are going to reduce it, so let's get to it. N squared divided by n squared is 1. This n is going to reduce one of those n's, and we'll rewrite it again. Here we go. Well, good gravy. I think we're ready to take the limit. How about you guys? So let's do this. The limit as n approaches infinity of 1, that's a constant, it's 1, divided by the square root of, the limit as n approaches infinity of 1 is 1. The limit as n approaches infinity of 1 divided by n, that is 0. We know that one. And then the limit as n approaches infinity of 1 is 1. Oh boy. Woohoo! We did it! I knew you could. Hopefully that made some sense and you're not totally lost. All right, let's move on. So those ones are actually pretty easy to manipulate sequences, but not all of them are. In the cases where it's not easy to manipulate the sequence, we could use the squeeze theorem. And we've talked about the squeeze theorem previously, but essentially if we can find the sequence and some sequences that are either much bigger or much smaller than them that do have a limit that can be found. So an easier one, easier to manipulate sequence, I should say. And if we can show that those two sequences on either side have the same limit, then the sequence that's in the middle has to have that same limit too. So I'm doing a terrible job of explaining it. Let's check out the graph. So here we see we've got three sequences, A, B, and C. And if we have a sequence A that's smaller than B, so this lower sequence, and if we have the sequence C that is above B, then you can see that both A and C are converging to some limit L. If B is in between both of those two sequences, then that means that B also has to converge to that limit L, because it's right in between them. And if they're both going to L, so does B. Sounded kind of bad. All right. Sometimes this is called, I think, the drunken policeman sequence. You can look that up. All right, so we have Gauss to thank for this as well. He didn't exactly invent it because we have evidence that Archimedes was actually using it, but he was the first guy to publish it, so he gets the credit, I guess. I said, let us go on. Okay, here we go. Example number 5. So here we've got the limit as n approaches infinity of the sine of n divided by n. So here's our method for using the squeeze theorem, right? We're going to find a limit that we do know, and then we're going to manipulate the inequality to create the problem that you're given. I don't know a whole lot about the sine of n divided by n, let's just say. But I do know a lot about sine. And I recall that sine exists in between -1 and +1, right? Our graph of sine is always in between -1 and +1. So great, we've got that. Unfortunately, this problem doesn't ask me about the limit as n approaches infinity of sine. It asks me about sine divided by n. So what I can do is manipulate this equation by dividing it by n. Of course, can't go around just dividing by n in one place. No. I also have to divide by n in all the sides. Interesting. Well, this creates a situation. It's got this situation where I know that the limit as n approaches infinity of -1 divided by n, well, that's going to give me 0. Okay, it's just coming up towards 0 from the negative side. And I also know that the limit as n approaches infinity of 1 divided by n is 0. And fancy that. We know that the limit as n approaches infinity of -1 over n is 0. And we know the limit as n approaches infinity of 1 divided by n is equal to 0. Then that means that if this is in between them, what's the number in between 0 and 0? It's 0. Yeah, it has to be the same thing. That's why we got the equal sign in there. So therefore, the limit as n approaches infinity of the sine of n divided by n must also have a limit of 0 by the squeeze theorem. Isn't that fun? I love the squeeze theorem. Let's try another. Ooh, all right. This looks a little crazier, but let's start with something that we know. Okay, I know that cosine exists in between -1 and +1. So let's try that. -1 positive 1, right? Right. But this is not a cosine of x. No, it is negative. It's getting added with 2. It's getting divided by x plus 3. Let's take care of these one step at a time. The first thing I'm going to do is make it negative. So I'm going to multiply by negative 1. Everywhere, it's a multiplying by negative 1 party. Everybody's invited. Here's what's going to happen. When we multiply by negative 1, our inequalities are going to flip because that's one of the rules for inequalities. So that's cool. Negative 1 times negative 1 is positive 1. I've got negative cosine x now. And negative 1 times positive 1 is negative 1. I'm going to flip my inequality. Great. I still don't have this guy. That's cool. I'm going to take care of this numerator first. Let's add 2. So I need to add 2. I can't just add 2 up here in the front. I'm going to add 2 here and add 2 here. So now I've got 2 plus 1 is 3. 2 and negative cosine of x. And negative 1 plus 2, 1. All right, it's looking good. We're getting it closer and closer. But now I need to divide the whole thing by x plus 3. I got that. Here we go. Easy. Divide it by x plus 3. Again, you can't just divide the middle part by x plus 3. You got to divide these end pieces also. All right, so now let's take the limit of these end pieces. Hopefully they're both going to converge to the same value. So let's check it out and see if we can show that. I'm going to take the limit as x approaches infinity, because that's what we're looking for, of 3 divided by x plus 3. Well, if x gets bigger and bigger and bigger, and we add 3 to it, that's still going to be super big, and we're taking 3 and dividing it by that super big number, that's going to get us a limit of 0. Similarly, this guy also is going to have a limit of 0. Since we know that this piece is in between these two, we can show by the squeeze theorem that the limit of 2 minus cosine of x all divided by the quantity x plus 3 also equals 0 by the squeeze theorem. I hope that you were able to follow how I was manipulating that. I actually thought it was kind of fun. I don't know about you. I hope you did. All right, I have one last one, and it's a little doozy, so pay close attention. We're going to use our logic here quite a bit. Whoa, 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 factorials? What? N to the n power? This is wild. This is a lot of n's. Don't worry. The first thing I want to do is try and make sense of the problem a bit. So I'm taking the limit as n goes to infinity, and it's going to grow and grow and grow. N to the nth power, and then n factorial is also going to grow. But which one's going to grow faster? You might know that already, but let's try and prove it a little bit more algebraically. So this is equal to, now let's take a look at the numerator first, okay? Your numerator, n factorial, that means n times, and then, well, you know, like 5 factorial goes 5 times 4 times 3 times 2 times 1. It's the same thing with variables. This is going to go n times n minus 1 times n minus 2 times n minus 3 times, and that's going to keep on going and going and going, and eventually you'll get to 3 times 2 times 1, right? Just like if we take 10 factorial, it'll be 10 times 9 times 8 times 7 times 6. Eventually, we're going to get to times 3 times 2 times 1. Every factorial ends up going there. We just don't know our n value. We don't know where we're starting at. Now, your denominator is n to the nth power. Well, n to the nth power is n times n times n times n times dot 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 n times n times n. So stretched out, this is essentially what is being said. We've got n factorial on top and n multiplied by itself n times, however many times that is, in the denominator. What I want you to look at is this chunk here, all of this. Do you notice that each numerator is less than the denominator? I should have typed it. When you have a numerator that is less than the denominator, it has to be, right? Because this is n minus 2 divided by n. Okay. Each time that you do that, you're going to get a smaller and smaller number. Think about it. If this is a fraction that's less than 1, and we're multiplying by another fraction that's less than 1, another fraction that's less than 1, it's getting smaller and smaller and smaller even. This is going to give us a pretty small number. It's going to be a shrinking number. Let's just make that note so we have it in our notes. Also, we should note that this is always going to be positive, right? This is 1. This is a number slightly smaller than 1. Another number slightly smaller than the last, slightly smaller than the last, but it's never going to be negative, right? So I'm going to make a statement about that too. So I got that lower limit taken care of, but what's larger? This is what I was thinking of. What is larger? Well, that's where we come back to this pattern that we were looking at again up here. Here, every numerator was less than n, right? But what if it was n? So then like n divided by n times n divided by n times n divided by n times n divided by n dot 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 off to infinity, right? Until we get to 1 divided by n. If we multiply all that together, it's got to be larger. It's got to be larger because here we were always multiplying smaller numbers together, right? But if we kept it n, that would be bigger. So this series would have to be larger. And check it out. I mean, these are just ones, ones, ones. I'm not going to show that here, but this is all ones. It's going to cancel out. It's just going to leave me with 1 over n. So 1 divided by n has to be larger. So what I can say here is 0 is less than or equal to n factorial divided by n to the n power, which also has to be less than or equal to 1 over n. Give myself a little bit more room. All right. Well, we know some things. Since the limit as n approaches infinity of 0 is 0, right? Because it's a constant. And do you see it? Is it starting to make sense? I hope you can see it right now. The limit as n approaches infinity of 1 over n is 0. Then the limit as n approaches infinity of that guy in the middle, n factorial divided by n to the nth power, also has to be 0 by the squeeze theorem. Isn't that great? Oh, I love math. All right. So it is also worth noting that the bottom of this denominator is actually going to grow faster than the top. And so as n approached infinity, this value down below is actually going to get much, much, much bigger faster than n factorial will. And so we could see that that was going to approach 0 as well. But I really liked my explanation of it. It was kind of fun. All right, guys, that's all I have for you today. I hope that the mysteries of the limits of sequences were revealed and that now you feel a little bit more confident using some of our strategies on the squeeze theorem. I hope you understood it. If you could please make sure you get your homework done, and if you would like to see the corresponding problems in our textbook, here they are. I especially like some of these problems from Jay, so you might want to still go in and try them. I hope you guys have a wonderful rest of your day. Have fun. Bye-bye.